Hey kids, Mr. Murray here on Mr. Murray's Math Land, another implicit differentiation video for you. Hopefully you're really getting the hang of this by this point. And this is, again, a kind of a twist on a classic question. You know, we've given the equation of a curve here, and we want to find the point or points, if any, where this graph has a horizontal tangent line. So we've seen this question before, and the strategy is exactly the same, right? The tangent line slope is given to us by the derivative, and a horizontal line has a slope of 0. So we're really saying, where does the slope or the derivative equal 0? That's really what we're asking whenever this question comes up, and shouldn't be really news to you at this point, but a little recap there. Okay, so the tricky thing, of course, is now getting the derivative can be a little more complicated because we have been encountering equations which are not in explicit form, not just y equals some function of x. No problem. Just going to use a little implicit differentiation now. Okay, so let's find this derivative. I'm going to take the derivative of this with respect to x. And the very first thing I come to is x squared y, so I got to use a little product rule for that. And again, maybe you're good at doing that sort of thing in your head. Maybe you need to, make the little chart here to help you organize. But a is x squared, b is y. A prime is 2x, that's x, so it's a normal derivative because you're doing the derivative with respect to x. Derivative of y, however, that's dy dx, or y prime if you really prefer. And so for your product rule, that's going to be 2xy plus x squared dy dx. So right there, just a little review of the product rule. Now moving along, the derivative of 3y cubed, that is 9y squared. And hey, we just did the derivative of something other than x, so I need to multiply by dy dx. Equals, and the derivative of 24, that's a constant, so that's 0. Okay, so we want to know where is dy dx equal to 0. That's our ultimate question here. You got to solve for dy dx first, right? So now you should be getting pretty good at this by the time getting to this kind of problem. So I'm going to do two things. We want a dy dx party on the left side, which means this is going to move to the right side. And I'm doing that so that I can factor this out. So I'm going to do the factoring and the maneuvering here in the same step. I'm going to factor dy dx out of these two terms and move that 2xy to the other side by subtracting. So I should have negative 2xy on the other side. And now I simply divide by that quantity. Dy dx is equal to negative 2xy over x squared plus 9y squared. Okay. So we got our derivative. Hopefully that wasn't too painful. And what painful, of course not. It was fun. It was amazing. And now the reason why we did it, remember, was I really now want to say, where does this derivative equal 0, if ever? And so when we set a fraction equal to 0, the only time a fraction is going to equal 0 is if the numerator is equal to 0. So that's really what you're solving here, is where does that numerator of negative 2xy equal 0? And it's already kind of in factored form, but that could happen two places, either when x is 0 or when y is equal to 0. Now be careful, that doesn't mean the point 0, 0. This means that the derivative will equal 0 anytime x is 0 or anytime y is 0. They don't have to both be 0, so we're not talking about the ordered pair, the origin 0, 0, at least not necessarily. Okay, so these are the two cases to consider, but we are looking for the points. If you go back to the direction, points, and that means ordered pairs. And so I need the coordinates that accompany each of these. And you want to do this anyway because I'm not even sure that x equals 0 is a solution for this. Maybe this has domain restrictions. So what I really want to do is think about, well, when does x equal 0, and plug it into this equation to find the corresponding y value that goes with it. Okay, so when x is equal to 0, let's see what does y equal. And so I'm going to plug 0 into this original equation for x, and so you'll get 0 squared times y plus 3y cubed equals 24. And of course, that's just going to make that 0, so I'm going to be left with 3y cubed equals 24, which means y cubed is equal to 8, which means y is the cube root of 8, which is 2. And so we did get a solution. We got the point 0, 2. I plugged in 0 for x, I got out 2 for y. There's that point. But now I do also want to consider, what about this case? When y is equal to 0. So I'm going back to the original equation here, if you need to scroll back here to see it. And when you plug 0 in for y, what do you get? So we'll have x squared times 0 plus 3 times 0 cubed equals 24. And as you'll see from that, that means you get 0 plus 0, which is 0, equals 24. And that is never true. There's no variable. So that just means that doesn't yield a solution. So that's telling you y is never even 0 on this curve in the first place. So your only solution is the point 0, 2. And a great way to confirm this, if you're ever unsure when you're doing your homework, not that you have this luxury on a test, is to check out the graph on your calculator, or in this case on Desmos, because Desmos is great for graphing implicit functions, because you can just type it in as is. And here is that function, x squared y plus 3y cubed equals 24. And you can see there's this horizontal asymptote at y equals 0. The graph is never going to get there. But it does have one horizontal tangent line at the point 0, 2, where that's got that relative maximum. And so a great way to confirm your algebraic results, because it's so easy to make a silly algebra mistake, but when you see it on the graph, it's a good feeling. So hopefully this made some sense and you saw a new type of problem. But if you have any questions, just let me know, and as always, keep working hard.